In this lecture, we are going to discuss time-dependent perturbation theory. So, we have been discussing time-independent perturbation theory till now, and we are changing gears here. Well, the basic equation of time evolution in quantum mechanics is, as you all know, the time-dependent Schrödinger equation. I h cross del del t of the state psi is the Hamiltonian operator acting on the state psi. Now, in order to do time-dependent perturbation theory, we are considering the setup that the Hamiltonian describing the system is made out of H0, which we, for the time being at least, assume to be time independent, plus V of t, a time dependent path, and H0 is a time independent, exactly solved Hamiltonian, whose spectrum we know completely. That means we know all its eigenkets, all these ket phi n's, and the eigenvalues epsilon n's. And these eigenkets are normalized and orthogonal, and they form a complete set, as you can see here. So this is about H0. V of t, which is going to be treated as a perturbation on top of H0, is assumed to be small in some sense compared to H0. We will see what small means in the course of the following lectures. Now, as we all know, the ket phi n's form a complete basis for the Hilbert space in question, which means that any general ket can be expanded in this eigenbasis of H0. So I can write our ket psi, which depends on time, as a linear combination of all the ket phi n's with coefficients an, and these coefficients of course depend on time. Now, substituting this in the time dependent Schrödinger equation, we get something rather simple. One term comes from the left hand side, which is IH cross del psi del t, and of course when you differentiate this expression with respect to time, it's only a and t which gets differentiated. That's why you have the a dot n t's here. On the other hand, you have two pieces, H0 acting on this and V of t acting on this. Both these are linear operators, so they will completely ignore the coefficients a and t and go and act on phi n. And H0 acting on phi n, of course, will give me epsilon n. V of t, of course, acts on phi n to give some new vector. So, in order to change this set of equations between vectors into equations involving ordinary numbers, we just apply the bra phi m, which of course is a linear operator, or sorry, a linear functional, which changes vectors into numbers. So, when you apply bra phi m here, this of course gives you delta mn. So, this gives rise to am dot t. This term gives you IH cross am dot t. And then on this term you get an epsilon n, again a delta mn, so this becomes am epsilon m. And this term of course stays a complete sum, because when phi m acts on this, I get the matrix element bra phi m operator vt ket phi n. And by simply changing sides a bit and dividing by this I h cross factor, I end up with this equation. So notice that this equation is an equation between a bunch of complex numbers. Now, everything here are just complex numbers. This matrix element, of course, is also a complex number. Now, if you look carefully at the left hand side, you can immediately recognize this is crying out for an integration factor, integrating factor. If you supply an integrating factor e to the power I by h cross epsilon mt, this left hand side is going to be a differential. And taking the cue from that, we introduce a new variable, that is not a new variable, but infinitely many new variables, one for each an. So instead of an, I'm going to use a new variable cn, which is an e to the power I by h cross epsilon mt. So basically, the left hand side here is the derivative of Cn dot, except for the fact that it's missing this exponential I by h cross epsilon mt. So the left hand side really is Cm dot t exponential minus I by h cross epsilon mt. And on the right hand side, all I have to do is change the ANTs here into CNT to the power minus I by h cross epsilon nt. And now we are done. Now, it's easy to see that you can rewrite this simply in this form. Let me just point out that you can move the exponential from the left to the right and take it inside the sum. After all, it depends only on epsilon m, so it's independent of the summation index. And as a result, what happens here is that in addition to this CNT and the minus I by h cross, ignore the double minuses here, there should only be a single minus, that's a typo. In addition to this CNT, what you have is an exponential of minus I by h cross epsilon n minus epsilon t, or plus I by h cross epsilon m minus epsilon nt. And this whole thing, once you take the exponential and the matrix element phi m vt phi n together and call that v tilde m and t, the equation simplifies to this: Cm dot is equal to minus I by h cross sum over n v tilde mn times Cn. Of course, both v tilde mn and Cn are functions of time. And what is v tilde mn? As I said, v tilde mn is simply this thing. You take the original matrix element, this of course is Vmn at time t, and you multiply that by the exponential additional factors, exponential I by h cross epsilon m minus epsilon t, and very often we also call this omega mn, this epsilon m minus epsilon n by h cross, the energy difference between the two states divided by the Planck's constant. And so this simplifies, at least the notation simplifies, to e to the power I omega mn t w v mn t. Here v mn, the omega mn, as I said, is epsilon m minus epsilon n over h cross. So this is a set of coupled differential equations, and not a very easy set to solve in general. You can of course rewrite this into the form of an integral equation. You could just formally integrate both sides of this to get Cm of t minus Cm of t0, which I have moved to the other side, is nothing but minus I by h cross times the integral of this thing at time t prime dt prime from t0 to t. Very straightforward. Now, is this a solution? Of course not, because the unknown quantities, the Cn of t, these unknown functions, are there on both sides of this expression. You have Cmt in this side, but we have the unknown Cnt primes on this side. So this really is not a solution. This is just a rewriting of the original differential equations, the coupled differential equations, in this form, which is a form of coupled integral equations. So finally we end up with this: Cm of t is Cm of t0 minus I by h cross sum over n t0 to t v tilde mn t prime Cn t prime dt prime. Now, while this is just the integral version of the equation, not really a solution, this does show us a way forward. What we do is simply this: instead of the Cnt primes here, we can just use the equation again, which means Cnt prime can be written down as Cnt0 minus I by h cross, again a sum, but now over another index of summation, n prime, let's say, and this integral will be not from t0 to t but from t0 to t prime, and v tilde of course will be v tilde mn prime at t double prime Cn prime t double prime dt double prime. So all I have done is I have just taken this expression which works for all the Cm's. I have written down this expression for Cnt prime and plugged that in place of this. So if I open this out a bit, I get that with Cmt0 minus one term which just depends on, it has only one v tilde, another term which has two v tildes but it has the unknown Cn prime stuck in here, Well, actually this is Cn prime at time t double prime, but then in place of Cn prime at t double prime, we can play the same trick. So that will be Cn prime t0 minus another term and so on. So if you only keep up to second order in v tilde, that is two v tildes, this will just be Cn prime t0, because the next term will have three vn tildes and so on. So what this integral equation allows you to do is that it allows you to simply write down an expansion for all these coefficients, which is in rising number of times v tilde is used. So this is a perturbation expansion, and if v tilde is small, then if we keep to the first few terms, it's usually quite okay. It gives us a very reasonable answer. In particular, if we just kept up to the first order in v tilde, which of course is proportional to v, we just get Cmt is Cmt0 minus just this one term, and this of course is second and higher orders here, which are being ignored. So in first order perturbation theory, the coefficients Cmt, which remember are just the coefficients which sit in front of the ket phi m, apart from the minus I by h cross epsilon mt factor in the expansion of psi of t. Cm of t is given by Cmt0 minus I by h cross sum over n integral from t0 to t v tilde mn t prime dt prime. This times Cnt0. Now we can specialize to the case when we start from a particular unperturbed energy eigenstate of H0, which means we are starting from the state phi I. Of course, that means that the Cn's, the coefficients at time t0, are all 0 except for the ith one, which is 1. So Cn t0 is delta ni. And if I substitute that, I get Cn of t is approximately delta ni minus I by h cross t0 t. The sum goes away because only one term in this sum survives, the one corresponding to n equal to I. And so we get v tilde, sorry, there's a typo, this should be v tilde ni t prime dt prime. This of course is for Cn. Previous equation was written for Cm. So Cmt is delta ni minus I by h cross t0 t v tilde ni t prime dt prime. So this is the simple form that we get from first order perturbation theory for the coefficients, assuming that we are starting from a particular eigenstate, the ith one of H0. Well, I hope there will be no confusion between this I, which of course is product of minus 1, and this I index, which refers to the ith state. Now, it might so happen that the perturbation may last for only a finite time and then go away. That is, your perturbation which is non-zero only over a finite period of time. If that happens, we can easily calculate the probability that the state initially in state phi I, which is an eigenstate of H0, will land up in the eigenstate phi k of the same H0, belonging to the same eigenbasis of H0, once the perturbation is over. Remember, before the perturbation came in, the Hamiltonian for the system was H0, and after the perturbation went away, assuming the perturbation goes away, so Hamiltonian is H0 again. So we are looking for an eigenstate of the system at distant past evolving into another eigenstate of the same system in the distant future. And for that, all you have to do is you integrate this quantity. After all, if it's a different state, then I and k are different, so this term is 0. These are the coefficients, so if you take the mod squares of them, then you get the probabilities. Of course, you should really take the mod squares of an's, but an, or in this case ak, but the difference between ck and ak is a pure time energy dependent phase factor which just cancels out. when you take the modular square. So probability that from the ith eigenstate you end up with kth eigenstate because of this time dependent perturbation is simply this quantity. Now you might say the integration should really be from t0 to t, or from when the perturbation started to when the perturbation ended, and you would be right. But since vki t is non-zero only over a finite interval of time, it does not matter if you take the integration interval to be that finite interval of time, or extend that all the way from minus infinity to plus infinity. So this is the result which we get from first order perturbation theory. You start with the system with Hamiltonian H0. There's a perturbation which comes in and goes away. You end up with a system again with Hamiltonian H0. So both phi i's and phi k's are actually stationary states of the system in the distant past and the distant future. But despite them being stationary states, there is a probability of transition from one to the other because the perturbation has come in. Of course, if there had been no perturbation, as energy eigenstate in the state phi I would always stay in the state phi I, just acquiring a phase factor as time goes by. It is the perturbation which makes this transition possible. And as you can see, the probability of the transition is proportional to the modular square of an integral. And what is critically important is that you have this vki of t here. So if the kith matrix element, the matrix element between the state k, phi k, and the state phi I of the perturbation happens to vanish, at least according to first order perturbation theory, there is no probability of transition to the kth state. Strictly speaking, that's not true, because that's only true in first order perturbation theory. In higher order perturbation theory, it may be possible to have a transition, but if the probability according to the first order perturbation theory vanishes, then the chance of transition, even if it is non-zero, will be much, much smaller than otherwise. So such transitions will be called forbidden transitions. So if vki of t were to vanish, that is, if the operator, perturbation operator v of t has no matrix element between the states phi I and phi k, then we will say that the transition from I to k is forbidden. Strictly speaking, it's first order forbidden, but for most practical purposes, such a transition can be assumed to not occur. Let us now consider another kind of perturbation. This kind that we just discussed is a perturbation which lasts for a finite amount of time and goes away. The next kind of perturbation I'm going to talk about is somewhat special. What it is that it's a perturbation which is zero in the distant past, as in our previous example. It changes over some finite period of time, but then does not vanish. Then it reaches a steady value, which we are going to call v of infinity, which of course means that once the time is large enough, v doesn't change at all. So whatever value it attains at infinity is the value which it has for all the time after its initial change. So what has really happened is that your Hamiltonian H0 changes to another time independent Hamiltonian H0 plus v of infinity in the distant future. So in the distant past, you have the Hamiltonian H0, as in the previous example. In the distant future, the Hamiltonian describing the system is again time independent. It's H0 plus v of infinity. So basically what we are talking about here is a system which had a time independent Hamiltonian in the distant past and had a time independent Hamiltonian in the distant future, but two different Hamiltonia, and v of t is essentially what makes one Hamiltonian change into another, but this transition happens over some finite period of time, so that if you're looking at this system at distant past or at the distant future, the system behaves as if it has a time independent Hamiltonian. So now, if we calculate the way the coefficient Cn's change, Ci in particular, the one in which the state in which you are in initially, the coefficient for that, well, it has a delta Ni, which is of course 1 in this case because it's delta II, minus I by h cross. The integral will be from minus infinity because t0 is taken to be minus infinity to the current time t. Now what you need is v tilde I t prime dt prime, the integral of that, but v tilde I is the same as v I. After all, the difference between v tilde mn and v mn is that there's an extra e to the power I by h cross epsilon m minus epsilon n times t term. That term of course is 1 for this. So this is what you have, and because you are looking at the system in the distant future, this integral of course it's a rather complicated integral. The integrand is 0 up to some time, then there is a time varying part, and then the integrand is steady at v I infinity for a long time. So if t is a long time after the perturbation has steadied out, this integral for all practical purposes can simply be considered to be v infinity into t. What that means is whatever contribution came to the integral before this time, we are simply ignoring that. So, and as long as t is large enough, that can always be done. So this is what Ci is. What about Cn or Ck, where k is not equal to I? Well, if k is not equal to I, the delta ki term is 0, and the rest is simply this integral v ki t prime into the I omega ki t prime dt prime. Now, what we will do next is we will try to change the integral from one involving vki to another involving its derivative. And it's obvious how you do it. You just do integration by parts, right? That changes a part of the integrand into its derivative. But the question is, why would we want to do that? And the answer simply is this, that for this function, v is 0 for a long time, after that is non-zero and changing, then is steady. But del v del t is 0 here, when the vt was constant at 0. It's also 0 here when v of t is constant at v infinity. So del v del t actually has support. It is non-zero only over a finite interval of time. So despite the fact that vki is actually non-zero over an extended infinite period of time, all the way from this time to, from the time it starts till the end of time, so to speak, del v del t on the other hand is non-zero only over a small region of time compared to the times we are interested in. And that might help us to do approximations much better. Of course, the way to do this is by using integration by parts, in which vki is to be taken as a so-called first function, the term which is differentiated, and the I omega ki t prime has to be integrated. So the integration by parts is rather trivial. Vki t prime into the I omega ki t prime integrates to the I omega ki t prime by omega ki t prime. There was a minus I by h cross already, and the I here cancels and you end up with h cross omega ki. And this whole thing is the integrated out part. Of course, the limits have to be put in, plus the other term which involves derivative of the first function vki and the integral of the second, the I omega ki t prime. The integral of course brought in this 1 by I omega ki, and you have this plus I by h cross, plus because of the extra minus sign because of integration by parts and so on, and this is what you get. Now the integrated out part is also pretty simple. After all, at minus infinity, far in the past, vki t prime vanishes, so you get only a contribution from t, and at time t, which is after the perturbation has steadied out, vki t is actually vki infinity. So this simply becomes minus vki infinity times the I omega ki t by h cross omega ki plus this term. So our expressions for Ci and Ck, that is all the k's which are not equal to I, are given by these. Ci is 1, nearly 1. The perturbation causes it to change from 1 to 1 minus I by h cross vi infinity Ck has one contribution from Vki infinity, and the rest of the contribution is actually from, although it looks like an integral from minus infinity to t, the contribution really comes from the small or at least finite period of time over which Vki changed with time. Now, by using these two coefficients Ci and Ck and going back to our original expansion, remember psi of t was sum over n an of t phi n, and of course what we replace the an of t by cn of t's, so there will be sum over n cn of t e to the minus I by h cross epsilon mt ket phi n. And from that sum, I have separated out the two different kinds of terms, one with n equals I, the state you start with, and that of course is going to be this. This of course is nothing but Ci in this case, Ci of t into the minus I by h cross epsilon I t. These together form the Ai of t, ket phi I, and the rest of the sum, which is of course sum over all possible k's except for k equal to I. For that you put in the Ck, which I just copied and pasted from here, times into the minus I by h cross epsilon k t phi k. Now we can sort of polish this a bit, and this term will leave as it is. This one we easily see also has this quantity, the I omega kit. Remember, omega ki is epsilon k minus epsilon by I by h cross. So if you consider the first term here, the minus I by h cross epsilon kt cancels, and you end up with the same factor, it is a minus I by h cross epsilon it here. And so clubbing them together, you get, this is the term you had originally, just this term. This sum is what you get from here. There is of course Vki, and h cross omega ki is epsilon k minus epsilon I. Because of the minus sign, this becomes epsilon I minus epsilon k, t to the minus I by h cross epsilon it phi k, and this whole thing here is an extra piece. Now, if you pay attention to my lectures on time independent perturbation theory, this may already begin to look familiar. After all, you can think about it this way. You started with the Hamiltonian H0, the Hamiltonian changed over time, but in the long run, the Hamiltonian is really just H0 plus V infinity, which means V infinity can be treated as a time independent perturbation to find out the spectrum of the Hamiltonian after a long time has elapsed. And in that calculation, this quantity should really strike a chord, because Vki by epsilon I minus epsilon k, this exactly is the additional first order correction you have to the state phi I because of the perturbation. This is Vki infinity. I should have actually perhaps mentioned infinity here, but that sort of is obvious. This is just something which comes from this term. So, in order to make this correspondence with time independent perturbation theory that we had studied earlier clearer, let me just point out a few more steps. One of them is simply this. Although this factor only multiplies this term and does not multiply this, I can play a simple trick. Remember, our calculation is being done only up to first order in V, so any higher order terms in V can be safely ignored. What that means is I can actually take this 1 minus I by h cross Vii infinity t to multiply not just this term, but the entire thing on the top here. Why? Because 1 times this is of course what this is, that's already sitting here, but the Vii infinity into this term will give you rise to something second order in V, and we simply can ignore that for the time being, because we are doing only a first order calculation. So that's what happens here. right? Just pointing out, that's the only change I've made. This was multiplying this term, I'm making it multiply the whole expression, and up to first order in V, that's perfectly alright. And then we play another trick. Of course, doing this actually has the advantage that this clearly shows you that this quantity is nothing but the new state, new ith state after the perturbation has been turned on, at least to first order in perturbation theory. This exactly was the result from time independent perturbation theory. Now, the prefactor here should also be pretty familiar. This is the unperturbed energy of an I. But what is this? We can actually replace this by e to the minus I by h cross VII infinity t. That might sound crazy, but remember we are again doing calculations only to first order. So first up to first order in V, the exponential and 1 minus I by h cross VII infinity t are exactly the same, which means that you can change this into an exponential, and once you have changed this to an exponential, you can combine the two exponentials simply to get this. And what does it tell you? It tells you that your state is this, the ith state has been changed to this, to first order in perturbation theory, and the energy of the ith state has changed from epsilon I, the unperturbed value, to epsilon I plus VII infinity, and that exactly is the result from first order perturbation theory. That's exactly how much the first order energy correction is. Remember the ith matrix element or the expression value in the ith state. So, for the time being, if you just ignore this piece is very familiar from time independent perturbation theory. This term is nothing but the ith energy eigenstate, but for the Hamiltonian at large positive times, that is for h0 plus v infinity, and this is nothing but the energy corresponding to that time independent Hamiltonian. Okay, just one more thing. Here you have phi k and it is minus I by h cross epsilon kt. Okay, so this term, the first term is e to the minus I by h cross epsilon bar I, where bar denotes whatever is the energy eigenvalue or eigenstate for the Hamiltonian at large positive times, that is once the perturbation has steadied out. So that again is the new time independent Hamiltonian whose spectrum is given by the eigenvalues epsilon bar I and phi I bar kets. So this is pretty easy to understand. This is exactly what we had in the top line here. Epsilon bar I here, the first order energy corrections included, and this is the new ket, unperturbed one plus the first order correction. So this one is easy. The second one that may take you a bit by surprise, what we are saying is I will change this epsilon k to epsilon k bar, this phi k to phi k bar, that is pertaining to the new Hamiltonian, the Hamiltonian at large positive times. But how can I do that? The answer is the bracket in front is already first order in V. If I were to change this epsilon k to epsilon k bar, I am incurring a change to the first order in V, similar to what we saw here. Changing phi k to phi k bar again is a change which involves first order in V. But since we are only calculating to first order in V and there's already one V term here, changing this to epsilon k bar and changing this to bar phi k makes no difference whatsoever. So this is what you end up with. And notice that this is exactly the time dependence which the phi I bar would have. Similarly, this factor gives you exactly the time dependence the phi k bar will have in the distant future when the Hamiltonian again is time independent, and these are just eigenstates of that. So we can rewrite them as phi bar it and phi k bar t, just time dependent energy eigenfunctions. But you see that you started with a state phi I at t equal to minus infinity. At time t, what you get is not only a new phi bar I state, but plus an additional contribution for other states as well. So the probability of transition from the ith state to the kth state is given by the mod square of this quantity. This again is a result which looks very much like the result we had derived a while ago for a perturbation which lasts for a finite time, but there is a very big difference here. Apart from the fact that, of course, that the expression is different. The real difference is this. There, the ith energy eigenkit and the kth energy eigenkit, between which we were talking about a transition, are eigenkits for the same Hamiltonian. Remember, the perturbation came and went away, so the Hamiltonian in both the distant past and the distant future describing the system, they are both A0. Here, that's not the case. The Hamiltonian in the distant past is A0. The Hamiltonian in the distant future is A0 plus V infinity. What that means is this transition I am talking about, the probability I to k, I started in the ith state, but the ith state of the Hamiltonian in the distant past, and I am trying to go to the kth state, which is the kth state of the Hamiltonian in the distant future, to a different Hamiltonian. But the transition between these two Hamiltonian eigenstates, which are both stationary states in those respective time domains, is given by this quantity. And before we finish, let us just look at what this quantity means, at least in two different limits. So if we consider a limit of very slow variation of v, that is del v ki del t prime is pretty small, and what constitutes very small? It simply means del v ki del, if it's very small, I can estimate this integral by just pulling this thing out, and then this integral into the I omega ki t prime, can easily calculate the integral, and if you do it, you will find that this is a sinusoidal integral divided by an omega ki, actually I omega ki, that comes out of the integration. And that means, the sinus of the order 1, this integral, the probability of transition for I to k, will essentially be much smaller than 1. If 1 by h cross mod omega ki, the mod is important because omega ki may very well be negative, times the magnitude of the rate of change, if this is much smaller than omega ki throughout, then this integral will be very close to 0. This is what you mean by slow variation. The rate at which the matrix elements of V vary must be much smaller compared to this quantity. The energy, which essentially is the energy difference between the two levels that you're talking about. And this is a special case of a more general result. This shows that if you start in the ith state and have a very slow variation in the potential, so that the Hamiltonian changes very slowly to another finite Hamiltonian, the probability of a transition to any other energy level is very small. Of course, the ith level itself changes as the Hamiltonian changes, but the system will stay more or less in the ith level if it starts there. This is an example of a more general result in quantum mechanics, which we will describe in a later lecture. This is called the Adiabatic theorem. If I change Hamiltonian slowly enough, then the system which is originally in an eigenstate stays in the corresponding eigenstate. Of course, the eigenstate evolves in time because the Hamiltonian itself is evolving in time. And we will later see that this is very important in describing many unusual and striking features, like say the Brady phase and so on. But the theorem is pretty easy to understand. If you change the Hamiltonian very slowly, then the system which is in the ith state stays in the ith state. On the other hand, if we change this very rapidly, what that would mean is del v ki del t prime is large over a very short time interval. Outside that is 0, of course. What that means again is that you have something called an impulse, a very rapid change. And in this impulse approximation, I can pull out the del Vki del t from this time derivative from the integral because, I can pull out it's the I omega ki t prime from the integral because over the very tiny narrow interval of time over which this thing is non-zero is the I omega ki t prime, which of course is a rather nice slow sinusoidal function, does not get time to change at all. And so Pi to k simply is, you just pull this out, t0 is the time at which this change is taking place, the small window centered around t0. So I can just pull down this factor, which is the I omega ki t0, and do this integral, which of course, if you do this integral, I will immediately get the answer from the fundamental theorem of integral calculus to be Vki at large positive times minus Vki at large negative times, which means just Vki at infinity. So after we calculate the mod square, we simply get Vki mod square by h cross square omega ki square. The probability that you start in the ith state and rapidly change the Hamiltonian and you're going into the kth state as a result is given by this. I will let you think about it, but if you think about how the ith state changes when you carry out time independent perturbation to the first order, it will be pretty easy to see that if you have a Hamiltonian which changes suddenly from one value to another, then in that small window of time, the wave function for the system does not get to change. So this is the impulse approximation. In the next lecture, we are going to take a look at the very important special case of a perturbation which keeps on going forever, basically a sinusoidal one. A sinusoidal one, perturbation is actually very, very important because there are many physical phenomena which are very closely approximated by this. In the next lecture, we are going to look at that. So bye for now.